Well, to start, I'd love to say a big thank you to the organizers of this event. This is my first conference and about to be my first talk, and it's been an absolutely excellent week, so thank you to them and thank you to all of you. So without further ado, I'm happy to be your closer. I'm Ivy Knudsen. I'm a post-bac working at the Southwest Research Institute with Dr. Kelsey's here. And we are currently collaborating on a paper and a project about small bodies in the solar system, and the first 2 points I'll breeze through because the third point is the main topic of this presentation. So we've been working on draping images from Simon Porter's new shape model of Arrokoth, which I'll show you on the next slide, to explore the line of small craters on Arrokoth a little better. So this is Simon's new shape model, and I just spoke to him today, which is submitted, so for the paper, so you can read more about that if you're interested. But moving on to comparing Arrokoth to the other small bodies in the solar system. So what bodies we use in this analysis and why? This chart is a chart of all the small bodies we have visited and imaged via spacecraft. And the green means we used it, the red means we did not, and if we didn't use it, it's because it failed to hit one of these criteria. Oh, I got it. Okay. So it didn't match one of these criteria. So the first criteria is that the body had to be imaged with a high enough resolution to see if any craters were present. So for example, this illuminated Larissa down here, really good picture of the size and shape, not so much craters. The second criteria is it had to be in the right size range. We were really only interested in small bodies. The two exceptions we made for this were Sharon, because we wanted as much data as we could for the outer solar system, which is pretty limited, and then Ceres, because there was really excellent high resolution data for Ceres. And then lastly, the craters had to be easily identifiable with high confidence morphology, so that eliminated, unfortunately, all of our comments, because as you can see here, this is 67p, and all of these features that are circled in yellow are picked from sinkhole depression and not the crater, and most comments had things like this, and it eliminated all of the crater, or all of the comments. And once we got our bodies, what are we worried about on these bodies? The crater size frequency distributions, which is mouthful, so I will say SFDs. And you'll be seeing this plot, this style of plot a lot, so just to break down kind of what you're looking at, this is an R plot of the differential values for the crater diameters. And it's based on this equation right here, which I'm sure a few of you have seen, but I wanted to put it up to emphasize two things. One, these are all normalized to a slope of -3, and so on these plots, a slope of -3 is going to be the straight horizontal line. The reason we chose -3 is because that's kind of the normal value that we would expect to see, and so normalizing it like this, you can see obviously any trends and deviations from the norm, quote unquote. And second is that it's dependent on the area of the mapped surface in kilometers squared. And that's important because it'll move these lines up on the y-axis because it'll reflect the spatial density of the craters, but not the x. The x is a direct reflection of the crater diameters for every one of these bodies. And on this is kind of you're kind of looking at everything that we've got here. So there are asteroids, KBO, small moons, dwarf planets, 2 larval piles, Ryugu and Bennu. But this is kind of a lot to look at, so let's split it up. So starting with the inner solar system, zooming in, you've got asteroids, the 2 larval piles, Ryugu and Bennu, and 2 Martian moons, Phobos and Deimos. And you can see here that they all tend to have a shallow slope, a little closer to -2, more so than to -3. Here's Ceres, which could average to -3, but in general, they all have this sort of shallow slope. And I divided the solar system into inner, middle, and outer rather than inner and outer because I wanted to pull these out specifically. These are really interesting to me, the really small crater SFDs. What's important to note is that these lines that all go back up that you're looking at are Saturnian satellites, which, shout out to Matt, explained that they get hit 7 times more than other small bodies. And I also wanted to pull middle versus outer to really emphasize the outer solar system here, Nix, Arrokoth, and Sharon, which all share this generally shallow slope as we go throughout the solar system. And looking farther, just to see if there are any trends between bodies, I've pulled out asteroids and then very small bodies. So these are the asteroids only, also have that pretty shallow slope trend. And then very small bodies, these were limited by Arrokoth as the upper bound because I wanted to pull one body from every classification of body we have, and Arrokoth being the smallest cold classical, this is the only cold classical we have a picture of, kind of by default set the size range on that to 35 kilometers, but they go down small enough as Bennu, which is about half a kilometer, all sharing this generally shallow slope. And so we have all this data, which is really great. So there's also a model, which is really great. So we want to see how well the data fits the model. This is the Bokeh collisional evolution model, or I'll call it the COEM. This is calibrated mainly off of the Moon and Vesta, because those were the best data that they had when it was made. And also worth noting that this is more or less arbitrarily placed. If every single one of these bodies was plotted with the evolution model, it would be in a different spot, but just to show the entire evolution model with the entire solar system, that's where I chose to put it. And so looking at the model with all of our data, this is all of our collection areas again. The results are that you can see that these values all have a pretty shallow slope, and they all just tend to deviate from the collisional evolution model and the predicted equilibrium slope of -3 to about -3.5. That's the Damiani slope that's predicted for bodies in collisional equilibrium. And whenever we get a picture of one of these past bodies, they are individually assessed. And this is not the first time this has been pointed out. So when each body is individually analyzed, it's been seen that the really small crater SFDs don't necessarily match the models at very small sizes, and so individual explanations can differ. So for example, a body could have been theorized to come from somewhere else in the solar system, or for example, Itokawa's interesting shape, it might have gone through a really large impact in the past, or Eros has different explanations for not only the lack of small crater SFDs, but an abundance of boulders. And while that definitely has merit for each body individually, we can see that this is happening on a scale of the entire solar system. So what could be making this happen throughout the entire solar system? Well, there are two main options. Small impactors can create craters and they can get erased, or there aren't really enough small impactors, so those small craters just don't get formed in the first place. And the first option is really plausible for asteroids, and it's really popular for asteroids, but the latter indicates that small impactors are fewer in number than what we predicted, and it's not quite clear why that would happen, but that's a motivation for this entire analysis, because the images of Arrokoth that we have are motivation to change it, because the shallow crater SFDs on KBOs like Arrokoth are a direct reflection of the impactor population, since they live in a collisionally cold environment. And the collisionally cold, shallow SFDs on KBOs are matching what we see in the inner solar system, so maybe we should, it was motivation to reanalyze maybe what's happening in the inner solar system as well. And so going through that first bullet point of erasure methods for craters that already exist, briefly going through some of these, the most popular, seismic shaking. Seismic shaking, something gets impacted, the seismic reverberations shakes up the body, can settle the regolith on the surface. The cookie cutter effect, new craters are overlapping old craters, they're taking transcendent cookie cutter. Further impacting, many small craters hit a larger crater, degrade the edges, degrade anything that could make it very identifiable as a crater. Ejecta burial, kind of similar for further impacting, except ejecta goes beyond the impact site, it can fill in or degrade smaller craters elsewhere. The York effect, this was brought in mostly for rubble piles. The rotation caused by radiation can cause it to spin fast enough that causes that regolith to slope down and either degrade or fill in smaller craters. And then sublimation and Oort cloud modification, these were exclusive to comets, but unfortunately, like I said, all of our comets failed that third criterion, we didn't have them. And so addressing some of the pathways that things, just trends to look for throughout the solar system to try to identify a cause. Addressing the distance to the sun idea, seeing if that has any effect. Here you can see where I divided the inner, middle, and outer solar system, but there's not super obvious trend in any direction based on distance to the sun. And the second one I wanted to look at was surface gravity versus the differential slope, seeing if there was any trends there. If we didn't have one, I also just calculated this myself with the irregular bodies with the errors accordingly, but also not super huge trend, not a super obvious trend between surface gravity. You can see this plot scales 5 orders of magnitude, whether the surface gravity or small body class. There wasn't a super obvious trend for either one of these. And another thing I wanted to look at, just going through possibilities for trends in these bodies, is we have plenty of these bodies that have one really large impactor. So here's 3, Matilda, Arrokoth, and Phobos. And I wanted to look at these just to see if the effects of seismic shaking, maybe if a bunch of small impactors wasn't enough to shake the surface, one big one might, or the cookie cutter effect, or to see if the ejecta burial of really large impact could go elsewhere. And so what you're looking at here is the same plot as before. It's the surface gravity versus the differential slope. And then in red are these bodies with one really large impactor, but also not a super obvious trend there either. And here and there are plots accordingly. And so what else? So those were some of the erasure methods and some of the other ideas we had. So what else could be causing these really shallow, small crater SFDs? Because erasure can certainly contribute, but it's not that convincing to account for all of these visible trends that we're seeing throughout the entire solar system. So a couple things that we've been thinking about, the small impactors could have formed what got ejected via the Yarkovsky effect, which basically summarizes that these projectiles of smaller sizes will move toward a resonant escape orbit throughout the solar system, often putting them on a planet-crossing orbit, which also has been proposed as the reason for the shape of the COM being the shape that it is, because these objects could have more heavily bombarding the moon than elsewhere in the solar system. Or another possibility is that these just aren't in collisional equilibrium yet. And not to say anything's wrong with the collisional evolution model, but the reason I wanted to bring this up is because the initial conditions could be changing with time. This was a really great paper that just came out last year with a new simulation for gravitational collapse of pebble clouds into planetesimals. And Polak and Clark 2023, they concluded that the process for collapsing a pebble cloud into a planetesimal is more efficient than previously thought. And there were a couple different conclusions for the amount of planetesimals, but something that I liked from their paper is that the amount of leftover material from the collapse of the pebble cloud decreases the amount of leftover material by about half. So not to say anything's wrong with the COM, but it is a possibility that these initial conditions that are being used are changing with time as more higher resolution simulations are made for all these dynamical processes. And so some future research. Like I said, we're writing a paper about this. We've identified some more trends and we discussed things a little more in depth there. So the paper about this topic is great with more models and more code to run, high resolution simulations, more for dynamical processes like the Yarkovsky effect, testing more initial conditions, identifying even more trends, which we've done a little bit more of. Scaling work, so moving backwards from craters, scaling back to actual impactor sizes, adding more COMs as they evolve. There's been one for the outer solar system as well. More spacecraft images, more small bodies to come, and of course impactor data sets from all the surveys you may have heard something about over the last week. And there's a summary. A vast majority of the small bodies crater SFDs for small sizes. They tend to deviate from the expected model, averaging around -2 rather than -3 or 3.5. Erasure methods for asteroids are plausible, but not for cold classicals like Yarkov. Suggests moving towards the idea that there's a lack of small impactors to begin with. And various methods for reaching that conclusion are still in consideration as we discuss in our writing this paper. So I would love to chat about it with any of you. And thank you for your time.
Questions? The microphone's on.
All right, or you can just talk really loud. Oh, that works.
I was just,
Whoa, that's a loud mic.
this was really cool. I liked it. So my first question is, there's now some codes that can be used. Dave Minton's working on Crater Maker, and Jim Richardson has his small body crater trend evolution model. I'm wondering if you thought about providing, say, a production function that can then be put into one of those codes to see if you can match what we see. So one of the things that they can do is do with seismic shaking and various other processes, topographic fusion, and it seems like a natural fit for trying to take these results and apply it elsewhere, or at least take those existing tools and apply them to Artifact.
I would absolutely love to get my hands on some code like that and work with it and apply it to this.
Let's chat.
Yeah, okay, great. I'd love to have it.
Great presentation, great work, and I know we chatted about this a little bit, but one thing that I I started to think about for a little bit of this was, this is all the small bodies, and I was just curious, you said like the slope was based off of cratering on the moon, and do people see this sort of difference in the slope in larger bodies that have cratering on them, or is that more similar to the moon?
That's a good point. I should have clarified that. So the coin that Rocky developed was based on the moon, but it's implied to be a direct reflection of the impactor SFPs of the asteroid belt, because that's kind of where that's where the impactors for the moon are thought to come from. And so looking at the crater SFPs on the moon, we can scale backwards to get an impactor SFP for the asteroid belt. So it's kind of a way to work backwards into small bodies just in the asteroid belt, and then we're extrapolating that to the outer solar system as well. Now, he did develop a new collisional evolution model for the outer solar system that came out earlier this year, but I just used this one for the asteroid belt because the shape is pretty consistent, and so I just left it at the asteroid belt.
Cool, thanks.
Great talk, Ivy. I'm curious, so you mentioned as an alternative to erasure, just a deficit of small impactors in the outer solar system, and you mentioned maybe Yarkovsky as a possible explanation for that. Have you considered what the time scale is for something not far away from the sun to get ejected from the solar system or transferred into a resonance via the Yarkovsky effect?
That is an excellent question. I have not, but I have initiated a discussion here about that very thing for all the codes that have been written about when the giant planets migrate, how that can throw things out of the outer solar system as well. So I'm going to explore that further for sure.
Thanks.
More questions? Okay.